Good, everybody. Right now, we are going to go into a topic called heat capacity. So, first of all, before we get into heat capacity, let's just talk about temperature and heat. So, temperature is just how hot or cold something is, and heat is just the transfer of energy from a hotter object to a colder object. So that's just like two topics that you know some people might be confused about, so I'm just clear this up real quick. So, when an object is heated or cooled, the quantity of energy that's transferred depends on three things. So, the magnitude of the temperature change. How much has your substance changed in your temperature? Two, the type of material. So, if we have, let's say, this piece of glass versus, let's say, this this metal fork. This metal fork is going to absorb heat faster than this piece of glass. So the type of material kind of affects how much energy is transferred to that object. And finally, the amount of substance. If you have like a tiny piece of ice cube, you might be able to melt it easily with like a tiny amount of heat. But if you have this giant ice cube, it's going to take more heat to melt it. So the amount of substance affects the energy transfer. Now, the heat capacity of a substance is just how much heat, or heat is denoted by this Q. How much heat do I need to give this substance to raise the temperature by 1 degree Celsius? So this C represents heat capacity. And as you can see, different objects have different heat capacities. For example, let's say that we have this metal fork, going back to our last example, and this piece of glass. They both start at the same temperature, and let's say we raise the temperature of this. We give both of this some heat, okay? Well, because the metal fork, it absorbs the heat faster, well, the change or the amount of energy that's needed for this metal fork to be risen, for its temperature to rise, is going to be less. So it's going to be a pretty low amount because it can absorb a lot of energy. So metals, they usually have a low heat capacity. And substances that absorb heat fast, they have a low heat capacity because the amount of energy they need, or the amount of heat they need to raise up their temperature, is going to be really low. Now, what about this kind of piece of glass? Well, because glass don't really absorb that much heat. So you're going to need like more heat supplied to raise the temperature of this piece of glass. So if the amount of heat that you supply, this increases, well, this is going to have a high heat capacity. This is going to have a high, I'm just going to write C, high heat capacity. So just to recap, objects that absorb heat easily, like this metal fork, have a low heat capacity. Objects like this piece of glass that have trouble, absorbing heat, this has a high heat capacity. So, specific heat capacity is just the amount of heat it takes to raise 1 gram of a substance by 1 degree Celsius. And things that absorb heat fast, they have a low specific heat capacity, and things that absorb heat kind of don't absorb as well, like a piece of glass, they have pretty high specific heat capacities. So the trend is kind of the same here. Now, specific heat capacity is really good for calculations. And let's show let's kind of do a practice problem using a really useful formula. So this formula, Q equals MCAT, or MC delta T. So Q is the amount of heat transferred, M is the mass of the substance, C is the specific heat of the substance, and your delta T is your change in your temperature. So it's going to be your final temperature minus your initial temperature. Now you might be wondering, what might this formula be used for? And let's show you an example. Say that we have this aluminum kind of cube right now, 20 grams, okay? It has a mass of 20 grams. Now we want to raise the temperature from 20 degrees Celsius to 40 degrees Celsius. And we want to calculate how much energy does it take to do this? How much energy does it take for this 20 gram of aluminum for its temperature to be risen by 20 degrees Celsius to 40 degrees Celsius? And we would use this formula for this. So let's define all our variables. So our mass is going to be 20 grams, 20 grams. Our C, well, we don't really need to write that because it's given to us down here, 0.897 joules divided by grams times Celsius, and our change in temperature. What is our final temperature? Our final temperature is 40 degrees Celsius. Our initial temperature is 20 degrees Celsius. So this is going to be your final temperature minus your initial temperature. So your change in your temperature is going to equal 20 degrees Celsius. And let's plug this into our equation. So just write this here. Q equals our mass, 20.0 grams, multiplied by our specific heat, which is 0. Specific heat of our substance. In this case, this is aluminum, so we're going to use this. So this is going to be grams times Celsius. And you're going to multiply this by your change in temperature, which is 20 degrees Celsius. Now, the answer you want to be left with in these types of problems, you want the unit to be in joules. And the way you know that you kind of done this problem correctly is if your Celsius cancels out, so the Celsius in the top and the bottom cancels out, and your grams cancel out. So you're going to be left with joules as your final answer. And let me just plug this into my calculator real quick. So okay. So we are going to get, if you plug this into your calculator, you're going to get 358.8 joules. But remember that we have to round to the correct number of sigdigs. In this case, the unit with the least amount of significant figures or sigdigs is this 20 right here, which has 2 sigdigs because it has this dot in front. So we're going to round our answer to 2 digits. So we're only caring about these 2 units. Take a look at the unit next to it. It is greater than a 5. So we're rounding up. We are rounding up. So this is going to be 360 joules. And that is going to be our final answer. So you can see how this formula is really useful if you want to calculate how much heat energy is required to raise the temperature of kind of a given mass of a substance by a certain amount. Let's talk about heating curves. So we're looking at a heating curve of water. And this just shows the relationship between the heat added to our water and the temperature of the water. So let's go. We are at our solid phase where we are this piece of ice. And as we add heat, the temperature slowly increases until it reaches kind of point B. This is where the ice will undergo a phase change. So this is when the ice will start to melt. So we are now at this phase. And as the ice starts to melt, so this is kind of like a solid liquid, you'll see something strange. Why is the temperature not changing as we add more heat for ice? Shouldn't the temperature kind of, the graph look something like a straight line like this? Well, this is because when we're kind of melting the ice, when this is going from a solid changing to a liquid, what we're essentially doing is we're weakening these intermolecular forces between the water molecules. So these forces of attractions between the water molecules. And this is what causes the temperature to kind of stay constant during a phase change. And you can see this as well in the liquid evaporating to a gas phase. So we can say that during a phase change, our temperature stays constant. So these phase changes, our temperature is going to stay constant. Now let's keep adding heat. Okay, so we are at this liquid phase. We are completely melted. We are at point C, and we are continuing to increase our heat. Continuing, and we are reaching our boiling point, which is point D. And you will see that, once again, to reiterate, this is going to be a straight line because now we're continuing to weaken the intermolecular forces until it's being overcome so that the molecules can escape into the gas phase. And this is kind of this phase right now where, the water is starting to evaporate into water vapor. And finally, in point E, we're kind of going back up. Temperature is going up. Heat added is going up, continually to point F. And point E is kind of the phase where all of the liquid water has evaporated. And what can we say about kind of the energy in the solid phase, the liquid phase, and the gas phase? What can we say kind of our what is happening to our kinetic energy during these phases? And what is happening to our potential energy during these phases? Well, because our temperature is increasing, right? We're adding heat and our temperature is increasing. So our kinetic energy is going up. But during these phases, we are not weakening these intermolecular forces during this phase. So the potential energy kind of stays constant. Now, what happens in the phase changes? So now we're talking about these. Now we're talking about the liquid to gas, solid to liquid. What is happening to the kinetic energy? And what is happening to the potential energy in this case? Well, our kinetic energy is going to be constant. It's not really going to change. It's not going to change because, well, we can see from the graph that the temperature does not change, which means our kinetic energy does not change. But as we said, we're weakening kind of the attractions between the molecules, so our potential energy is increasing. And the way I like to remember this is the lines that have kind of a slope. Those are the lines where the kinetic energy is increasing. The straight lines, so we can see segment B to C, segment D to E. These lines, this is when the potential energy increases. And there's one more thing. Now, you might have noticed that there's all these formulas here. And what are they used for? Well, this is kind of, let's say we have this like 20-gram sample of ice, and we're trying to completely melt it into water. How will we calculate how much energy is needed to do that? And in this case, we're going to use kind of the BC segment of the graph. Why? We're going from the solid to a liquid. So like this, we're trying to do a phase change. We're trying to undergo a phase change. And this is kind of the segment of the graph where the solid is undergoing a phase change into a liquid. And therefore, we would use the formula that is underneath this. All we do in this formula, very simple. Take 20 grams, 20.0 grams. So our mass of kind of our substance. And we're going to multiply this by the heat of fusion, which is 334 joules per grams. And you see how when you get your answer, the grams will cancel out. So you're going to be left with joules, which is exactly what we want. So if I just plug this into my calculator, we're going to get 6,680 joules. But remember that we have to round to the correct number of sigdigs. This has the least amount of sigdigs, which is 2. So we're going to round to 2 sigdigs. So this is going to be 6,700 joules, which is going to be our answer. So just to recap, kind of the non-phase changes, so like segment AB, segment CD, segment EF, you're going to use Q equals MCAT for those problems. And for BC, segment BC and DE, so the phase changes, you're not going to use Q equals MCAT. And for those of you wondering why segment DE takes more energy or takes more heat to vaporize the water, liquid water, than to melt the solid ice, well, that's because when you're kind of melting ice, you're only weakening kind of the intermolecular forces. But when you're transitioning from a liquid to a gas, you're kind of completely breaking the intermolecular attractions between the molecules, which is why it takes more energy or heat. Now we are asked to calculate the amount of heat energy required to raise the temperature of 30 grams of liquid water from 20 degrees Celsius to 60 degrees Celsius. And looking back at our heating curve, which formula should we use? Well, because there's a change in temperature, you see, we're changing our temperature from 20 degrees Celsius to 60 degrees Celsius. And whenever there's a change in temperature, we're going to use Q equals MCAT, okay? So just kind of remember this. Whenever there's a change in temperature, you're most likely going to use Q equals MCAT. In this case, we are going to use it. So our change in temperature, well, let's first define our variable. So our mass, well, we know that's 30 grams. So let me just write this down. 30 grams. Our specific heat, which is our C. Well, because this is liquid water, look at our chart right here, specific heat capacity of water, and we see that liquid water has a heat capacity of 4.184 joules divided by grams times Celsius. And finally, we have our change in temperature, which is just 60 degrees Celsius minus 20 degrees Celsius, and that's going to be times 40 degrees Celsius. Now you see how our Celsius cancels out, our grams cancel out, we're left with joules, and that's what we want. So if I just get a calculator, 30 times 4.184 times 40, we are going to get 5,020.8 joules. But we have to remember to round to the correct number of sigdigs. In this case, take a look at the one with the least amount of sigdigs, which is the 30. So I'm going to care about these two units. Take a look at the next term. Our answer is going to be, we're going to write this in scientific notation, actually. For this problem, 5.0 times 10 to the third power in joules. Because if you were just to write it as 5,000 joules, you would see that you would only have one sigdig. Or if you were to write it as 5,000 with a point, there's 4 sigdigs. So just to get the correct number of sigdigs, you write it in scientific notation, and you wouldn't write it like this. And yeah, that's the answer. Now we are asked how much heat energy is required to completely vaporize a 30-gram sample of liquid water. So as you can see here, you're not really given any temperature. So what you want to do right now, so basically, if you were to kind of look at it from the heating curve we were talking about, our temperature is staying constant. And all we want to do is go from a phase change. So we want to go from a liquid, and then we want to go from liquid to a gas, right? And when we undergo a phase change, if we're trying to undergo a phase change, we're not going to use Q equals MCAT. Why? Because when we're undergoing a phase change and we're looking at the heating curve, our temperature stays constant. There is no change in temperature when you're going through a phase change. And instead, we're going to use the heat of vaporization formula to solve this problem. And this is very similar to the heat of fusion. It's very easy. Just take 30 grams, 0.0 grams, so the kind of mass of your substance. I'm sorry, I forgot to put a decimal there. And we multiply it by the heat of vaporization, which is 2260 joules divided by grams. The grams cancel out. You're left with joules, which is what we want. And we're going to get 6,700 and then joules. Remember, we have to round to the correct number of sigdigs. So look at this. 2 sigdigs. Look at 2 sigdigs here. Take a look at the next term. This means that we're rounding up because this is greater than a 5. So we're going to get 6.8 times 10 to the 4th power in joules. And that is going to be our answer. So you see how we've rounded to 2 sigdigs here, and there's 2 sigdigs here because of the dot. A 200.gram sample of liquid water at an initial temperature of 20 degrees Celsius absorbs 50,000 joules of heat energy. What is the final temperature of the water? And we're given the specific heat capacity of liquid water. Now, so we start off with this 20 degrees Celsius of water, we add 50,000 joules, and we're trying to find out the final final temperature. Now, because we're solving for the final temperature of the water, and we're given an initial temperature and how much energy it's absorbed, we know that there must be a temperature change. So this is why we're going to use Q equals MC delta T, because we know that there's a temperature change from absorbing this much energy. This is not going to be a phase change because of the final temperature of the water. This is what we're going to be given. This is what we're given. So now we're given our Q, the energy absorbed, which is 50,000 joules. And this is going to be equal to our mass, which is 200 grams, 200 grams, times our specific heat of water, which is 4.184. This is also given to us, divided by grams times Celsius. But this time, we don't know what our change in temperature is. This time, we don't know what our change in temperature is. We know that our initial temperature, we know that our initial temperature is 20, but we don't know what our final temperature. Let's call our final temperature X. And our change in temperature is just going to be X minus our initial temperature. Because we know that the change in temperature is the final temperature of the water minus our initial temperature. So because our final temperature of the water, we don't know it, and it's X, this is going to be X minus 20 degrees Celsius. Minus 20 degrees Celsius. Okay. So the way, I like to do it first of all, I'm going to multiply these two parts together. So the 200 grams and the 4.184 part, and we get 800. So the grams will cancel out, and we get 836. 836.8, and this is going to be joules divided by Celsius now. And now we're going to multiply this by X minus 20 degrees Celsius. And obviously this is going to be equal to our 50,000 joules. Just going to pretend that it's there on the other side of the equation. We do some distributive property stuff, and we're going to get 836.8 joules divided by Celsius. So this is going to be X minus, and then this is going to be, the Celsius will cancel out. So this is going to be 836.8 times negative 20, which is negative 16,036. So, sorry, so this is going to be 16,736, and this is going to be in joules, and this is going to be equal to our 50,000 joules, right? 50,000 joules. Now, what we want to do is we want to isolate our X, right? We want to isolate this part of our equation. So what we do is we add this part on both sides. And when we do so, we are going to get, so 50,000 joules plus 16,736. We're going to get 66,736 joules equals 836.8 joules divided by Celsius X. Here's X. Now, if we want to isolate X, divide this by on both sides. So divide this on both sides, joules divided by Celsius, and we divide it here, 836.8 joules divided by Celsius. And you'll see that the joules cancel out, so you're going to be left with Celsius, which is what we want, because when we're finding the final temperature, we want it to be in Celsius, right? So since the joules cancel out and these cancel out, and we're going to be left with X, because this whole thing cancels out since we're trying to isolate this X, we're going to get X equals, and this is going to be 66 divided by 136.8. We're going to get 79.71751, and then a whole string of numbers. But remember that we have to round to the correct number of sigdigs. And when we take a look at our kind of beginning, we can see that our initial temperature is 20 degrees Celsius. So we're going to round to 2 sigdigs. Sorry, I forgot to put the dot there. But we're going to round to 2 sigdigs. So we're focusing on these 2 units. Take a look at the next one. And we're going to get X equals 8.0 times 10 to the first power Celsius, or 80 degrees Celsius, but because of sigdigs, we write it like this.